줌에서 제 목소리 들리실까요? 채팅을 확인해 봐야 되나? 아, 감사합니다. 감사합니다. 네, 그럼 저희 이제 yeah, 영어로 해야지. We're gonna start the next session. And the next session will be about the hands-on programming. So, let's go to a repository here. This is what we're gonna do today. So if you brought your laptop, then please visit this repository and fork this to run this on your computer. Actually, I am gonna use the GitHub's code space, and I think this works pretty well. So if you didn't bring the computer, maybe you can just take a look at the screen together. Okay, I'm done. Okay. I share the link. And if you click this code here, recently, I think it recently launched this code space. I'm not sure it's been long, but you can open this repository and set up a Visual Studio, Visual VS Code on your web browser. And if you fork and launch it, this code space, then what you have to do at first is just installing the dependencies. So maybe you can see the README file and just type yarn on your terminal. Then it will install the dependencies. Actually, I already installed everything, so maybe it might take a little bit of time for you guys. Okay, so and if you already installed every dependencies, then let's try to run some tests. The maybe actually not only in this Web3 industry, but also you always have to take care of the test-driven development. So we're gonna start running tests here. And the test code is in the test directory. So here is the test code. What I wrote for today's lecture is just deploying a smart contract and checking that it has a address for its returned object. But we are not gonna take a deep look at this only. We're gonna take this one. Okay. So what I'm gonna do is just introduce a simple grammar of the Solidity about how to write this one. So we have a at first constructor. This means when you create a smart contract, you can add some parameters, and also simultaneously, you can also execute something there. So here we are executing a logging, and it is just, printing that in our terminal. But you should be careful about this using console log. Is only for dev tooling, so it is not used in the production. Okay, so then what we can put into the constructor as parameters. For example, how about adding some string value? String name, and maybe we can store the string inside of blockchain like this. And by the way, it is shadowing the parameter, so we can add a underscore there and store the given parameter into the storage variable. So actually it's not completed yet. So if we assign some variables here, it means it's a storage variable, which means these values will be stored in the Merkle-Patricia tree of the account that we have seen. Like, you remember, we have account and storage root, and if we define some storage variable, then it will be stored here. Yeah, but when we write the parameters, actually we should define where this data exists, because it's also a giving some transaction. So an account should execute a transaction from that account, which means it has a transaction data. So this name parameter is also a part of the transaction data. So we can explicitly write down that, okay, this is from a call data. Call data means a data inside of a transaction, raw transaction. That means the call data. But actually we have a some other types of data types. For example, let's write a function to change the name. For example, like function change name, like this. It means when this contract deployed, the name will be stored in a storage variable. And if we execute this function, the storage variable will be changed. So name should be changed, like new name, right? But here, what I want to talk is about, okay, then how can we concatenate or how to deal with the strings here? So if you want to make a new string, then we can define a new string value here, but you need to explicitly write down the modifier. For example, if it's a storage variable, you should write down just like storage. Storage name to change equals should be a storage variable. Here, the storage variable is name because name is defined just under the contract, so it is a storage variable. But if you write down like these, actually it will make a compile error. because new name is not on the storage. It's a cold data variable. So the where the data exists is different with the names changed to and the new name. And the other data type we can use is the memory. So for example, cold data is a data inside of the transaction. But if you write down if you just define another variable on memory, then and also if for its next step, if you assign this cold data to this one, it means we're gonna secure some slots, memory slots, to store some value here and load the data from the cold data area to the memory. So Solidity has a kind of some modifier to explicitly define where the data exists, but you don't need to write those kind of data modifiers for some primitive types. So because the reason is because string usually cannot be a primitive type because we cannot expect the size of the data, right? But if we can expect some size, then we use those kind of types mostly as a primitive type. So I'm gonna just delete all the lines here. So then what kind of a primitive types will exist in Solidity? It's definitely about numbers, right? Number. And unsigned integer 256 means 256 bits, which is a 32 bytes. So actually we can convert this unsigned integer into a bytes value pretty easily. And when you write down this primitive types, you don't need to write down the explicit data modifier. So for example, if you want to update the number, you don't need to define the cold data memory storage here, but actually you can still use the storage verifier too. Here we can use just like this, but actually the data here, this _num is in the cold data area, and this is just storing the data from loading from the cold data and storing that to a storage area. So these are kind of a primitive types we have, but it's not enough to write down all the programs. So what we have is definitely the list and dictionary, right? So we can have a type of list type or dictionary just using a keyword mapping. Keyword mapping needs a two type definition. One will be the type to be used as a key value. So for example, if you want to write down, if you want to store some value under your account, then maybe we will use a primitive type just like address. And then under your account, what we are gonna store that? Maybe your balance. Then it becomes like this. Then we can name the variable like balance. Okay. And for the next, maybe let's try to write some functions, and maybe let's try to figure out what kind of access modifiers for functions exist. I'm gonna delete all this one. So actually, you don't need to write that. Actually, you can just follow this. So, okay. Let's say we have only one variable, and we have a one function to update the variable here. And for this function, we can have a three types of access modifier. And actually, if you don't define the modifier, it just becomes a basically becomes another modifier which names internal. But actually, our code convention is writing down the access modifier every time for every function. So the first modifier is definitely public. And what is the opposite of public? Private, right? Private. And also, actually, we have a something like protected in Java. You know what is protected in Java, right? We can use that in the inherited class. So in Solidity, the access modifier, which is similar to protected, is called internal. So we have these three kinds of modifier. And then let's see the difference between those modifiers. So imagine what do you think about this public modifier? What does that mean? It means someone can execute this function, and internal and private is not allowed to execute from the external. Do you remember how to execute a transaction for a smart contract? Actually, I said, like, when you want to execute a smart contract transaction, we need to match the function name at first. It means in this contract's application interface is exposing only this function name. And how to expose this function name is about, we only take the first 4 bytes, which is a hash of the function with its parameter types. You don't need to know about what is the ABI in CodePack here. So this is a kind of some bad things of how Solidity is bad. Right? So by the way, we have a 4 bytes of function selector. So when you want to execute a transaction, then you put the 4 bytes in front of your transaction data, and then put the parameter data behind of this function selector. In this case, we need to put a 32 bytes of integer data. Right. So let's see, like the call data will look like 4 bytes. Yep. 4 bytes of data. This is the function selector. Actually, it will not look like this. Or like this. So, and then the number. Let's just imagine the number is like 10, then 0, 0, 0, 0, a padding and 10, because it should be a 32 bytes, because the primitive type is unit 256. So this is how the transaction call data look like. So if you send this call data to the address count, to this KAIST Bitcoin contract address. If you send this data to this contract, then you will be able to execute this function. This is how transaction works. Yeah, but we need to see some other modifiers too. So I'm gonna just remove this data again. Okay. That is about the other types of function. Actually, this function is changing the state, right? But there are functions, something like immutable function, which will not change the state, which will not change the storage state. They are called pure or view function. So the difference between pure and view function is, for example, there's a pure function which returns a name. And the name here is like KAIST. This kind of function is called pure function because it doesn't access to any kind of storage variable, right? So it is just only a code and it executes and it doesn't need to check any storage variable, or it doesn't need to change the storage variable. So it is the kind of most cheapest function type, function style. On the other hand, there kind of also a view function exists. Public view returns maybe u integer because we are not storing string value here, and it returns a number, which is a storage variable defined here. So it is reading a value from the storage and returning that to you. It should be much more expensive than pure function, because if you want to read some value, then the execution clients are more than multiple thousands clients in the world should do the same thing. Okay, where's my database, and where's the index, and where's the value, what is stored in that index, and returning that to you. So this should be kind of a much more expensive action compared to pure function. Okay, and for the next, let's imagine if someone sent a transaction to this account with a real function signature and some weird data like this. So in this case, we do not have this function selector in this application interface, right? So in this case, we can define a fallback function when some transaction request doesn't match a existing binary interface. Then we can log like you're calling a non-existing function, etc. But actually, this pattern is commonly used for when you create some contract account, because we need to do something for every kind of a transaction request. Okay. Okay, so I think we took a pretty quick look at the Solidity grammar and how to write some Solidity program here. Maybe, do you have any other questions for about the Solidity here? Okay. If you don't, let's go to the other topic. The easiest way you can try the Solidity programming is going remix.ethereum.org. You can write some smart contract code on the browser, and you can see some examples here. And also you can compile that here using this compiler menu. So it will compile, and also you can deploy and try to run a transaction using this remix page. So I'm gonna share this to the chat. Also, for actually people do not use remix for their production. What people usually use is two dev toolings right now. One is Foundry, which is based on Rust, and the other one is Project, which is based on JavaScript and also TypeScript. So if you want a faster environment to test your contract, maybe Foundry might be a good choice for you. Or if you want to make some dApp front-end application together, then Project will be pretty helpful for you to make some application together. Okay, then let's go to the example. So today, what we are gonna implement is KAIST's own Bitcoin. So maybe you guys are already forked this repository, right? And then we're gonna start for this mission. The mission is implementing Bitcoin on top of Ethereum. So we have some requirements here. First one is a miner will get the mining reward by proof of work, which is a very traditional technology, right? And also it will be implemented by using the ERC20 token reference. So we're gonna go through it. Okay. Okay. Actually, I just prepared branches for our tutorial, hands-on tutorial. So the first one is the first step is implementing the electric curve signature to verify your Bitcoin transaction is valid. So actually, I didn't explain the structure, the type of struct. So Solidity also has a struct keyword to define some types inside of it. So it just works like TypeScript. So you can, if you write down like type something equals like this, it's the same with the TypeScript. Oops. And I prepare the default structure of the Bitcoin transaction. So let's see. What Bitcoin transaction should include? Definitely the sender, recipient, and amount to send. And actually, we also need some fee to give to the miner. And also, we need a signature that the sender agreed on sending the Bitcoin, right? So the transaction should look like we have from, to, amount, fee, and signatures. Okay, then for the next step, we're gonna validate transaction. And to validate transaction, actually, we need to compute hash function here. Let's go to implement the others here. Okay. I want to use the live share together. So if you want to come into this code space, you can come here. So let's start. To validate a signature, we usually sign something using a hash. So there should exist a transaction hash, and we're gonna compute how the transaction hash looks like inside of this function. So we can consider, okay, this function will return a transaction hash by computing here. Then, okay, great. Let's try to write down how the transaction hash should be look like. So we are gonna just hash all this data. That's all. That's easy, right? We're gonna hash all this data. So we're gonna use hash function catch-up here, and to provide the data into this catch-up hash function, we need to encode every data into one byte. So transaction will have an amount transaction will have the transaction will have the from value, and transaction will have a to value. Transaction will have amount value, and transaction will have a fee value. So, yep, that's all. So we are implemented the how to compute the hash of a transaction here. So this function will return a hash function correctly. Then actually this is something that you can skip, because we are gonna use the Ethereum library to sign some message, and Ethereum library always puts some prefix in front of a hash message. So hash to sign is something a prefix plus transaction hash of hash value, something like. But actually this will not work. So I'm gonna use another external library here. The external library is the Open Zeppelin library. So this Open Zeppelin library is a commonly used reference for people. They started as an auditor company, and they audited a lot of smart contracts. So it is considered de facto, considered a reference implementation of a smart contract. And what we are gonna use from their reference is the ECDSA smart contract implementation. ECDSA is stands for elliptic curve digital signature. So it is just using a elliptic curve point to make a signature, and this is about the implementation of how to verify the signature is correct or not. So especially in this library, we're gonna use this one, the to each sign message hash. You can see we are concatenating a prefix and a hash message and hashing that again here. So this is commonly used Ethereum standard to sign a message. So we're gonna use this function, and you don't need to worry about this assembly. This is only for optimization, so you don't need to know about how the assembly code works here. So I'm gonna import the ECDSA smart contract. It's like this, ECDSA. And oops, I imported the trade something different. Nice. Okay. I'm gonna import them here. So we can use ECDSA. And then hash to sign will be look like ECDSA's to each signed message hash and transaction hash. Okay. And for the next step is recovering the signer from the signature, right? We need to figure out who signed this message. Actually, that feature function also exists in that same library. ECDSA that recover hash to sign and the signature inside of the transaction. It will return the signer's address. And finally, we're gonna add a constraint here that transaction sender should equal to the signer, right? Definitely. So we're gonna add a constraint signer should equal to the transaction sender. This statement means if this condition is not true, it will be reverted. So for the reverted means, for example, we are just doing something here, something like we were just modifying some storage inside here, but if this requires statement revert this transaction, every state transition occur during this transaction will be canceled. Okay. Okay, and actually I'm gonna return some value here, Boolean, that just to check we implemented this function well by testing. So if it doesn't return any value, it becomes a little bit difficult to test. So we return some value here. Let's try to compile the source code we write works well. You can like yarn compile. Okay, let me just go through quickly for the scripts defined in the package.json. So there's a compile command, and it uses hardhat dev tool, and it lets compile the smart contract inside of this contracts directory. So if you just write down yarn compile, hardhat will compile all the contracts inside of this directory. Let's try to compile. Oops, it means we have some issue. Hash to sign, recover. What's the problem here? Hash. Oh yeah, thank you. Thank you, Joseph. Hash to sign. Great. Joseph just fixed the code, and let's try to compile. Great. Thank you, Joseph. And then how should we write the testing here? Let's go to write some tests. Okay, go to KAIST Bitcoin the test here. And I'm gonna actually just checking the contract is deployed is not that meaningful. So I'm gonna change this test code to a validate transaction. And to just mock and test the transaction validation, we need to write a the transaction building stubs. And actually, I already prepared building transaction using JavaScript inside of the utils, the TypeScript. So we can use this function. In this function, we put signer to amount and fee, and then make some object, and then create a transaction hash, and then let the signer sign a message and get a signature. So yep, get a signature and returns a transaction with signature. So in the test, we can just simply write down like, but we need a signer here. So I'm gonna define two more accounts, Alice and Bob here. And Alice and Bob also, we can just mock some accounts using dev tool here that get signers. And I will let Alice sign a transaction message. So a transaction should look like build transaction. And in the transaction, we need to put signer. Alice will sign this. Okay, good. Alice will sign this. And Alice will send something to Bob. So 2 is Bob's address. Amount equal should be a something, but how can we express the fixed points in Ethereum? Actually, Ethereum does not have a floating type. So we only deal with bytes, everything, bits. So we usually use the concept decimals. So if the decimals is 18, then 1 means 1 to the e minus 18. And if the decimal is like 6, 1 means e to the e minus 6, and 100 means e to the minus 4. So we are using some utility parse either to express either to a something like this value. Yeah. Actually, 1 ether is like 1 to the e, 1 e to the 18 is 1 ether. And let's give a fee here, parse ether. And let's give 0.01 ether to the miner. Okay, great. But actually the build transaction function is returning a promise. We need to wait the result here. So the transaction will look like this. Okay, great. And then let's send this transaction to the deployed. We have a deployed contract here to the deployed contract, validate transaction. It will return some value. What do you think what value this contract will return? That is this Boolean value. And actually it is only returning true. So it should return a true there. So we are expecting this result to be true. Okay, I think we completed to write the test code here. And let's try to run test. Here in test. Oops. Some problem. Yes. Okay, so you can see our test code is passing the validate transaction test code. Okay, we've completed the step 1. Let's go to the step 2. the step 2 is about implementing the proof of work. So if you're familiar with how proof of work runs, proof of work is something that you randomly pick a value and hash the block header you want to mine with this random value together. And then we will finally have a hash value. But we have a constraint here. If you want to submit that successfully using the proof of work, the hash value should be less than some value. For example, you hash some value, then let's see, is the value less than 10? Maybe not. It will mostly greater than 10 in most cases. But is it less than 2 to the 254? 2 to 254 is only 1/4 of a 32 bytes, right? So maybe if you just try to make some hashes, then maybe you're gonna find some value which is less than 2 to 254. This is how the proof of work works. Actually, I don't think it's important, but this is traditional technology. We're just started from the Bitcoin blockchain. So we're gonna implement the proof of work here simply. So to start that, we have to see the we have to define the block header first. So from the session 1, we just took a look about how a Ethereum block header looks like, right? Then now it's the time to define our own block header. So the block header can be pretty simple because it's a blockchain. So just put previous header, and if you mined a block, you should get the reward. So just put miner address here. And this nonce value will be used to prove your proof of work. And in a block, you also should include the transactions. Actually, we already implemented a transaction, right? We should include those transactions inside of this block. So this block header will also have a transactions record. Okay. Then, okay, so here, this is a kind of a skeleton of the validate block header function. This should validate this header includes correct information inside of it. So for example, just like transaction hash, let's assume we have a hash function to hash the block here. And we're gonna verify here previous header equals the last submitted block. So which means if you submit a block, that will be recorded in the smart contract. So we're gonna define some storage variable here. The first storage variable is the block header hash, which is submitted at the last. And when we validate the block header, the previous block header should equal to the stored block. Does it make sense? Right? Does it make sense? Okay. And also for the next step, we're gonna validate the proof of work too. So validating the proof of work will require only block hash and the nonce inside of the block header. Okay, so we're gonna implement proof of work here. So what I said is we're gonna just hash the two values. The two values are block header, block hash, and the other one is nonce, right? And actually we need to include these values to provide into hash function. So, let's assign this hash value into the variable which name is val. Oh, I just forgot that maybe there is a possibility that we can have a multiple Bitcoin implementations on Ethereum, right? So to prevent some double spending between those potential other contracts, I would like to add one more inside of this hash, that is the address of this contract. This is what I want to add here. Okay. And what is the requirement? The requirement is it should be smaller than a certain value. And the certain value will have its own difficulty. So I'm gonna define a difficulty here. So we have some difficulty. So difficulty will start from 0. So it will go 1, 2, 3, 4, 5, 6, 7, 8. So we will increase the difficulty when people mine Bitcoin too fast. Okay, let's go here again. And then how to compare this value with the difficulty is pretty simple. It should be something like this is the biggest value inside of this machine, and we're gonna shift it to the right using difficulty. Yep. So if difficulty is 0, this hash value should be less than this one. It will be definitely less than this value. If difficulty is like 16, to the like, then it will like something like this if difficulty goes up, right? So I'm gonna write this with a more fancy grammar using and it will look like this. So we implemented the proof of work using a simple hash function. Then, okay, we also implement some block header hash, but I'm gonna just use a previously written one. Okay, let's try to compile this code. Let's see. It will be compiled. Oops, one more error. So, no, line number 39. Let's see what's the problem. Oh, We missed one. This right? Or is this right? Oh, we need to convert the type. Okay. Let's compile again. Okay, it's compiled. And let's try to write up a test code for this. For the testing, actually, we also have a function, utility function to find the nonce for this proof of work. So I'm gonna bring that from the another branch. Just a moment, please. In the utility, we're gonna define the header type too, and we're gonna have a block mining source code. Let's see how it works, the how to mine block here. So to find the correct nonce, at first what we have to do is having the header hash. And the how to compute the header hash is just using miner, previous header, nonce, and transaction root. So until we find the correct nonce, we're gonna pick a random value and then compute the header hash, and then hash the header hash with the address of the contract and nonce value. And if that satisfies the condition, we're gonna mark mined boolean to as true and gonna break this while loop. And then we're gonna return this value, return the block header value. Then it will find some nonce value after some tries. Then for testing, we also should write down some test code here. I'm gonna add one more account, which name is miner. Okay. It's miner in, let's add one more test case here. The test case will validate header. And inside of the test case, we're gonna check the previous header. And previous header should be fetched from the smart contract, right? We have a last block variable inside of the smart contract. And I should say for about the public modifier for the storage variable. Here, the tip is if you have a public verifier, it automatically creates a viewer function for this variable. So if you just add public modifier, then it will increase the code size because we need to create a view function for this variable, automatically created by the compiler. So because we have this, it will have a view function for last block automatically. So we can fetch from the smart contract for the last block data. Then it will return the previous header. At first, it will something like 0 bytes. And also we should fetch the difficulty too. And then Actually, we do not have a transaction validation logic yet. We're gonna just pick a random bytes for transaction root because we are not validating it yet. So we are almost ready to make a block header. So using previous header difficulty, we're gonna use this mine block utility function to find the nonce. And it will something like address will this contract address, and difficulty will be the fetched value. But actually the fetched value is a big number object because we cannot deal with the 32 bytes number inside of our computer, our architecture. So we are having another some object class for big numbers. So we need to convert this value to a primitive type, and we're gonna assign transaction root. Oh, it says it's a promise, so transaction root, and actually we can skip this one, and miner should be miner's address, and then previous header will be previous header. And also actually we can write down like this. Okay, I hope this will create a valid header by finding a right nonce through the proof of work. Then let's try to check the results from the validation function. So validate header, block header, and we're gonna just put this header inside of it, and we definitely expect this result to be true. And let's try to run this test. Still buggy. Test 32. What's the problem? Yeah. I forgot the function modifier. Yeah. Why is it returning false? Okay, let me validate POW. Oh, it is not returning any value. So we should, we should return true here. Then validate block header will return true here. Let's try to run. Run test. Oops. Something happened. Yes. Okay, great. It says it took 0.721 millisecond to find the nonce, right? So maybe if we increase the difficulty, it will take a much more time. Well, let's try to increase that. Like currently this is 0, but we can increase the difficulty by assigning a value like 3. Okay, like 1.561 milliseconds. Maybe if it's like 6, it'll take a little bit more, I guess. 24.3 milliseconds, like. So I guess, okay, the proof of work seems pretty well here, right? Okay, and then for the third step, we have 4 steps. So 10 minutes per one step. So for the third step, we're gonna implement this as a working smart contract using the ERC20 reference. So if you execute a transaction, it should transfer token from the sender to the recipient, right? So we're gonna extend a ERC20 here. We're gonna import ERC20 smart contract from Open Zeppelin reference. So Open Zeppelin has a reference smart contract for ERC20. So and we're gonna extend this ERC20 contract for this our Bitcoin implementation. And you can see the compiler is showing some error, compile error, because ERC20 this reference implementation has a constructor with some value parameters. So we also have to define our own constructor to just extend the ERC20 function. So what we have to do here is, okay, let me define a constructor here. And actually, maybe we can define some initial difficulty, and also we should fill up the parameters of the parent smart contract. So parent smart contract needs the token name and its symbol. What should be our token name? What should be our token name? It's the easiest question. Yeah. So by the way, this live share is not working. Okay, KST, great. Name should be KAIST Bitcoin or KAIST Bitcoin, KAIST token in our student suggested KST for the symbol, token symbol. So we can select, define like this. And then for the next step, let's execute the transaction. So here we can define a transaction, a function to execute transactions, and we're gonna receive a transaction list as a parameter here. And when we execute the transactions, we're gonna transfer fee to the miner. So you're gonna add miner's address also as a parameter, but this will not be executed from the external account. So I'm gonna define this an internal function, and we need to loop, right? for example, for I equals 0 until it's less than transactions length, and adding 1. But actually, this is not guess efficient because this statement will be executed every time when we just looping this loop. So it means we always try to read the length value from the memory. So it will increase your gas cost. So I'm gonna define another value and assign that here. And use it again, use it instead of that. Then using this, we can just reduce gas a little bit. And we're gonna transfer, right? We're gonna transfer it's a transact from the transactions sender to the recipient, right? And amount should be the same one in the transaction data. And also, we're gonna send some fee to miner too, right? And fee will be defined in the data too. So we wrote down the executing the transaction, right? Okay, for the next step, let's try to mine a block, which means mining a block will validate POW, validate header, validate transactions, and execute these transactions and write down the last block, right? That is mining here. And mine function should be available for everyone. Everyone should be able to execute that function mine. So I'm gonna write down mine just like this. And here, actually, I prepared another struct for a block. So it is just a set of header and the transactions. What we already wrote down the validation code. So here we're gonna get block as a parameter. And then at first, we're gonna validate block. And then for the second, let's try to increase difficulty if the block period is too short. And record the block, record the last block time just to compare the block period, and also execute transactions. And then we should mint some token to reward the miner. So we will mint token and reward this to miner. And then actually we're gonna add one more new concept here about, not a new concept, we are gonna log a KAIST Bitcoin is mine. Okay, let's try to write down the exact working code. So for the first we are not validating the block here. We are only validating the block header. So what we have to do is changing this validate block header to validate block. So I'm gonna change this like this. Okay. And block hash will be the block hash of the header inside of the block object. And we can write down like this. And what do you think that we are missing here? What is the thing we are missing? We are not validating the transactions, right? So we have to validate transaction. We have to validate transaction, right? So to validate transaction, we are already wrote the validating function. So we're gonna just put the transaction object inside of the validated transaction. And one more thing, what we are not doing here is about the checking the transaction root. So we should compute the transaction root from the list, which is a implementation of a Merkle tree, computing Merkle tree root. And I'm gonna just bring the Merkle tree root implementation. So it's we're gonna have a Merkle tree root implementation here. So it means if you put a list of transactions into this function, we're gonna hash the transaction and get the hash values and set it as leaves for a Merkle tree. And we compute the root of the Merkle tree by so if you have some Merkle tree like this 5 leaves, then how we can compute the multiple root is we compute a parent node of the first root, and also this one. But actually, this is an odd. It doesn't have its sibling. Then we just have 0 value leaf and compute the parent hash, and also repeat this going just up to the level to the depth, and we can compute this one, but actually it doesn't have its sibling. So just put 0 here again. It's 0 and compute the parent, and it's like this. This is how we compute the Merkle tree. So this implementation is including that logic inside of it. So we can compute transaction root, and finally, we're gonna validate this transaction root is equal to the transaction root inside of the block header. Yep. Yep. Actually, we have only 4 or 5 minutes, so I'm gonna jump to the completed branch to check the result. Okay, this is the finally completed code for implementing the Bitcoin. So actually, for the mining function, what we tried to write down was first validating the block. So in validating block, we check the block header, and we check the transaction root is correct, and we check the proof of work, and we check the transactions. And then if we finish the validation, we check the last block time, the block period is too short. If it is, we increase the difficulty. And then we log that the difficulty is increased here. And also log, store the last block time to just compute the block period, and then execute transactions and mint some value and give this minted token to the miner. And yeah, finally, this is the complete version of the KAIST Bitcoin. And for the final stuff, let's check the how test codes does look like. So we have a first block here. So the miner will mine a Genesis block here. And the miner now has a minted token. So the miner can send this token to Alice and Bob. So for the second block, the miner creates two transactions. So miner gives Alice 0.1 Ether and also Bob 0.1 Ether, and just mine the second block. And for the final result, we can check that something's mined and Bitcoin is transferred from miner to Alice 0.1 Ether, like this. So for the final step, let's run this code and finish the lecture. Okay. Yep. That's all. Thank you so much, everyone. Yep. So is there anyone who has some questions? I'm sorry. Yeah. So actually, I am gonna have some chimek today with, if you are interested in joining together. So if you're interested in just stay here and let's move together.